Today, we're going to talk about a number that has puzzled students and thinkers for centuries. It's a number that sounds like it belongs in a fairy tale, but as we're going to see, it's actually baked into the very fabric of our reality. So let's dive in.
All right, let me start with a question that probably made you cringe back in math class. What is the square root of -1? I mean, your calculator says error, your intuition screams impossible, and for a very long time, the entire mathematical world totally agreed.
In fact, the very name we use for these numbers today, it was originally meant as an insult. Back in 1637, the great philosopher and mathematician René Descartes coined the term imaginary just to dismiss them. He was basically saying they were fictitious, useless, not real.
But what if we just pretended it exists? What if we invent a new number and we'll call it I with just one simple rule? I squared equals -1. This one simple, seemingly absurd definition? Well, it's the key that unlocks a whole new dimension of mathematics.
And look, if you think this all sounds a little nuts, you are in very good company. But here's the thing, we've been here before. This exact same skepticism once surrounded a type of number we now use every single day without a second thought. Back in the 1700s, serious mathematicians were asking questions like, how can you possibly take 4 cows from 3? How can you have less than nothing? The whole idea of negative numbers was just considered absurd. One critic even said they darkened the very whole doctrines of the equations. It took this huge mental shift to see them not as tangible things, but as a super useful tool for describing relationships, like debt. And this is the exact same journey I was about to take.
So you might assume, right, that this imaginary number was invented just to solve that simple equation from the start, x squared equals -1. But the real origin story? Well, it's way more dramatic and, honestly, a lot more surprising than that.
Imaginary numbers weren't born from those simple little quadratics. Nope. They were the unavoidable byproduct of this fierce battle to solve much tougher problems, cubic equations. And these were equations with very real, very tangible solutions that, bizarrely, could only be found by taking a detour right through the imaginary world.
Oh, the history here is like a soap opera, seriously. In the 1500s, you had Italian mathematicians locked in public duels, and these bitter rivalries all over a secret formula to solve these cubics. When Girolamo Cardano finally published the method in his masterpiece Ars Magna, he stumbled on this really weird paradox. For some equations, the formula forced him to calculate the square root of a negative number as an intermediate step, even though the final answer was a perfectly normal real number, like 4.
Cardano himself called it mental torture. He would just have to work with these impossible numbers, watch them magically cancel each other out, and then somehow arrive at the correct answer. He couldn't explain why it worked, only that it did. It was like a mathematical ghost in the machine. But it took another mathematician, Raphael Bombelli, to finally sit down, lay out the rules, and show that these imaginary numbers, when you handled them correctly, were a legitimate, powerful tool.
So, for centuries, I stayed as this strange but useful trick. But the real breakthrough, that big aha moment, came when mathematicians stopped asking what I is and started asking what it does. And the answer wasn't a quantity, it was an action.
To really get this, we have to expand our view of numbers. We're all used to the number line, right? Stretching from negative to positive infinity. But what if there's another dimension, a vertical axis? This is what's called the complex plane, where the real numbers live on the horizontal axis, and the imaginary numbers get to live on the vertical one.
Okay, here's how to think about it geometrically. Multiplying a number by -1, say you take 1 and multiply it by -1, it flips it a full 180 degrees across the number line to land on -1. So the question becomes, what operation, if you do it twice, gives you that 180-degree flip? Well, the answer is a 90-degree rotation. And that rotation, that very movement from the real axis up to the imaginary one, that is I. Multiplying by I is simply making a 90-degree turn.
And this reveals this beautiful, elegant pattern. One 90-degree turn gets you to I. A second 90-degree turn gets you to -1, which is exactly what our definition, I squared equals -1, said it should be. A third turn takes you down to -I, and a fourth brings you right back to 1, completing the circle. It's this perfect 4-step cycle, which makes I the ideal tool for describing anything that rotates or repeats.
So this whole idea of rotation isn't just some neat visual trick. It's an incredibly powerful tool that makes really complex problems simple in the real world, from navigating a boat to the electricity that's powering your screen right now. And the practicality of this is just stunning. Imagine your boat's position is 3 units east and 4 north. We can write that as a single complex number, 3 plus 4i. Now, say you want to turn 45 degrees to the left. You don't need complicated trigonometry. You just multiply your position by a specific rotation number, and that simple algebra instantly gives you the new heading, -1 plus 7i. That's it. You're now 1 unit west, 7 north. The rotation is baked right into the math itself.
This gets even more profound when we look at electrical engineering. See, in an AC circuit, the voltage and the current aren't always perfectly in sync. There's often a phase shift between their waves. To describe the total opposition to the current, which is called impedance, you actually need two pieces of information: the resistance, which is kind of like friction, and the reactance, which is related to that phase shift.
A complex number is perfect for this. The real part represents the resistance, and the imaginary part represents the reactance. And here's the payoff. By combining both magnitude and phase into a single number, engineers can transform a complete nightmare of differential equations into a simple algebraic formula that looks just like Ohm's law. Voltage equals current times impedance. It turns incredibly difficult problems into simple arithmetic.
And here's a fun fact that just proves how essential this is. In electrical engineering, they don't even use I. They use the letter J instead. Why? Well, because I was already taken as the symbol for current. They literally had to invent a new letter just to keep things straight because they use complex numbers that much.
So, I started out as an insult. It became a mathematical trick, then a powerful engineering tool. But the story, it doesn't end there. The final, really mind-bending revelation is that I isn't just a convenient fiction. It seems to be a fundamental part of the universe.
This right here is the Schrödinger equation. It's one of the foundational equations of quantum mechanics, describing how matter behaves at the tiniest, weirdest scales. And right there, you see it, is the imaginary unit, I. Now, in classical physics, like with the circuits, you can always find a way to rewrite the equations without I. But in quantum mechanics, you can't. It's not optional. It's absolutely essential.
For a long time, physicists wondered if I was just a necessary quirk of the math, or if it was truly representing something deep about reality. Could you, in theory, create a version of quantum mechanics using only real numbers? That question hung in the air for decades, until very, very recently.
And this is amazing. Physicists actually designed an experiment to test this exact question, and the results were conclusive. They calculated that a universe governed by a quantum theory using only real numbers had a theoretical limit. The maximum possible result in their experiment was 7.66, but when they ran the actual experiment, the result came back at 8.09. It smashed right through the real number barrier, proving that our reality requires complex numbers to be described accurately.
The conclusion is just inescapable. As physics today put it, there is no version of quantum theory using only real numbers that can correctly describe our universe. The I that Descartes mocked as imaginary is, as it turns out, fundamentally real. So we're left with this thought, right? We went from a number that was considered impossible to a convenient tool, to an indispensable part of our most fundamental description of reality. It really makes you wonder, if a number we literally named imaginary is essential to the universe, what other profound truths are hiding right in front of us, just waiting for the right perspective to be seen?